SwayamPrabha. Digital India. Educated India.
Students, yesterday we were talking about the various translation motion, rotational, and the general plane motion. So that is the general approach. But even before that, for the sake of completeness, I also have to talk about a little bit of analytical approach. Analytical approach in the sense that we formulate the equations for displacements, maybe the linear or angular displacements, and then simply we go through the differentiation with time to get velocity and another differentiation with time to get acceleration. So this is obviously, as you can say, when such relations can take place. So those situations will arise only when the problems are simple. But however, let's just take up a few examples and then see whether something can be. What are those examples where we can handle it in a completely analytical manner? So let's just take a few examples. So a few examples. So essentially what it means is that you should be able to handle the problems in many ways, either the graphical ways, for example, you can draw the polygons, or analytical or semi-graphical. So depending upon situation, you may take up any method. So but however, you should be conversant or you should be an expert in all these methods. So just as an example, so let's take a rod here. A rod here. So maybe of length L, and so this is a rod is resting on the floor above, on 2 floors. And if this, so they're not attached, so let's assume that the end A here is tied to a string here, and then we say that it's going over a small cylinder. This is all, of course, not very much necessary, but however, for the sake of practicality, so we can say that this end A is tied by a string and then going over a cylinder here of radius some r, and then it is going through an angular velocity here. So end A is tied to a horizontal string, pulled by a motor. Okay, this is like a narration. Okay, and then you're supposed to find out the motion of A is known, so the motion of B is supposed to be known. For example, if it is moving with an angular velocity here, uniform angular velocity, this is a very simple problem. So if this is being pulled, then this is supported here. So as it is being pulled, so you can see that it will take some other position here after some time. So after some time, maybe you can say that A prime, B prime. Okay, so that looks like that, A prime, B prime. And then, well, now I've shown a lot of this motion, but it can be in small steps. Okay, so our task is to find the velocity of point B, which is having a length of L. Yeah, so to do this one, so let us see. So let's find out the angular velocity here. So this is angular position theta. So we will let's just find out what is the angular velocity. Instead of doing this, we might do it later. And let us simply say that we're trying to find out the angular velocity of the rod. Okay, so to find out this one, so so if you call this as some value here, a distance x, maybe you can put xa. So we know that xa is nothing but, so this is analytical approach. So where we formulate it in the form of formula. So the distance xa here is nothing but some r omega, where r is the size or the radius of the drum, and omega is, so let us say this is some omega naught. Given omega naught, so we can find out okay, so that's I'm sorry, this is actually angular velocity. So let us say, so angular velocity multiplied by this one will give you the linear velocity here. So before that or after that, so let's say that the distance xa here is given by h times xa is h by tan theta, or we can even say h is okay. So this is the basic relationship between the distance xa, which is variable, as well as the angle theta. So both of them are functions of time. And so what we would like to do is that we would like to differentiate with time. So if you do that, then on this side, so we have h is constant, so dh by dt is 0. And then So this we keep constant, and this we will differentiate it. So it's secant square theta dot. Okay, so this is what is the relationship. So this dx by dA is nothing but VA, and this is tan theta, and this is XA. So theta dot is omega, and so this is how we can write. So omega here, if you want to find out, it's a very simple expression. So at any particular time, so we know what is the theta value, and then you substitute that here, and you know the velocity here. In fact, the velocity here is, we should also be consistent with the positive directions. So if XA is measured from this thing up to this point in this direction, so the velocity here is going to the left, and so we can put it as a minus r omega, and here we can put a minus here, and if you want to write that here, minus VA, so it's r omega tan theta. Interestingly, so omega, I'm sorry, this is r omega naught. So interestingly, you can see that this is negative, but this angular velocity is positive, which means that as A is moving towards to the left, so the theta is going to increase. That's why the angular velocity here turned out to be positive. Okay, so that's how we can do it. And so the we'll just finding out the angular velocity. We can do many other things. For the moment, we'll leave this here, and then we will take up some other interesting problem, a similar kind of another example. Yeah, another example. Again, a kind of rod, but here, this time, so here we have a rod is attached to two blocks A and B at the end of it, and then we would like to find out here, given the velocity of this one, so knowing the velocity of A, motion parameters, so velocity and acceleration A, that means that to be A and A to find VB. Okay, so this you might have seen in some of your exams, I suppose, but however, let's complete this one. So then how we do it here is that we want to relate A and B. So here A, let's represent by at a distance of x, and this we will represent by y. Okay, So we would like to find out y. This also you can represent by theta. So and then this has a velocity given by VA. Let's assume that that's given to us. So we'd like to find out BB and AB. So let's do that. So for that, so let's try to get a relationship. Y is equal to, you can say, x tan theta. That's one way of doing it. Okay. Or another type of thing is the relationship between this is a relationship between x and y. We can directly write it like this. So this is more convenient. X squared plus y squared is equal to L square. And then we would like to differentiate this one with respect to time. So differentiate it with respect to time. So if you do that, both x and y are functions of time, while L is constant. So we can do that. So it is 2x x dot and 2y y dot is equal to 0. So x dot and y dot are the velocity of A and velocity of B. So it's very clear now. It's very easy to find out. So the velocity of B, which is y dot, so y dot here is nothing but minus x by y times x dot. Okay, so which means that the velocity of B is nothing but x by y. So at any position theta, if you want, we can even x by y, we can write it, or y by x as tan theta. So this also can be written as VA by. So we can also write it in this manner. Okay. So then you can also go one step further, and then you can calculate the relationship between the accelerations. So same thing here. So this thing we will take. So one more differentiation. To get relationship between accelerations. So for that, so we'll drop this x. So that means that here x and x dot are a product. So obviously both are functions of time. So it's x dot plus x double dot y dot and y double dot. So given the accelerations of A, so that means that this is x dot square. Let's simplify that. And x times acceleration of A, right? And this is y dot square. So VB square and y times VB. So just writing the accelerations in terms of accelerations. And so here this is very easy to find out. Acceleration of B is nothing but this is x dot square. So this is VA square. X into acceleration of A minus VB square. So you can write it in this manner. So this is VA square x into AA, VB, yeah, plus VB square. This is what it is. And by y, and everything put with a negative sign. Okay, so at any instant, if you want to find out the velocity of B and acceleration of B in terms of given values of velocity of A and acceleration of A. So this is how we can do it, right? So these kind of problems are very much amenable, and we can apply. Okay. So what is the advantage of this one? So the advantage of this one is that you can program it, these expressions, and then write down the whole velocity and acceleration profiles. Okay. So as theta changes from say some theta naught to all the way to 90, so you can find out what is the velocity and accelerations, how they change as functions of theta. Okay, so that's the advantage here. So now let's another example, simple example. Example 3 is a very common example. Okay, so this is a crank and connecting rod mechanism. So wherein we have a crank here, so this is about reciprocating engines, pumps, and so on. So where this crank here, as it moves with certain angular velocity here, or including acceleration, so then this B here, the piston, which will move in up and down oscillatory motion, not necessarily simple harmonic. Okay, so if you are given the angular velocity of this crank, so is it possible to find out the B? So this particular problem will take up again and again in many situations. So right now I'm going to do it through the analytical way by direct application of these relationships, including trigonometry. So what we have here is that so obviously if theta is changing maybe at a uniform rate, so we have the angle here is changing at some angular velocity omega, and then we would like to find out the velocity of B. To find velocity of B. Okay, so what we have here is that so you can very well see, so if you can find out, obviously B is moving up and down here, so you can call this as some distance x. Okay, so x denotes x is equal to B, and now this x is a the vertical, on this one, projection of this crank and the connecting rod onto the y-axis. So this x is now, you can see that it is r cos theta plus L cos phi. Okay, so this is L F phi. So both theta and phi are changing. Okay, and then if you want the velocity of this one, obviously, so velocity of v is nothing but dx by dt, and we can do this minus r sine theta, theta dot L sine phi, phi dot, because phi is also a function of time, theta is a function of time. So we have to relate again, we are given theta dot, which is omega, and sine theta and all that depends upon the instantaneous value of the crank position. So how do we write this phi and in terms of theta? So for that, so we can see that the r sine theta, so we have a geometric relationship here. So r times sine theta is equal to, we have the relationship of projection of this crank on the horizontal line, so which is r sine theta is L sine phi. So this is the angle. So that means that if you want phi, so from here, if you, for any theta, if you want phi, so we can find out phi is nothing but sine inverse of r by L. So it's possible to calculate. Okay. And on the other hand, we also have phi dot here. So for that, we had to differentiate it, this one. So differentiating with time. Yeah. So differentiating with time. So we have this r cos theta, theta dot plus L cos phi, phi dot. So phi dot now can be expressed from this as okay. So this is about phi dot. So using this now, so we can substituting this in above relationship, in above equation. So we get VB as minus r sine theta, theta dot is given to be omega to us, and minus L sine phi, phi dot, which is here given by okay. So this also can be replaced by omega. So we can omega like this one, right? So like this, so we have given omega, so we can find out the velocity of the piston as this. So knowing given a theta, so you can find out phi from this relationship, and from that you substitute phi into this relationship, so to get a VB in terms of omega. Okay, so this also can be extended to many times. We are interested in the acceleration later. So many times, if you want, we can even have the relationship for accelerations. Okay, so for that, what is that? We have here, where is that? So that means that if omega and alpha is given, okay, if crank also has angular acceleration, so alpha, which is nothing but u omega by dt. So here we have VB like this one, right? So we can take this relationship, okay, and this relationship. So this is the virtual relationship, which might you use it to get phi, but this relationship between the first derivative of theta dot and phi. So you take this one and differentiating this above equation. So if you want, you can even number it. This one, 1, 2, 3, and this is 4, 5. So differentiating 4 again, okay, and this one VB, 2, for example, 2 is the 1. So differentiating 2, so we have acceleration of B, which is nothing but dV by dt. So we have, now it's a function of 2, so it's minus r sine theta is cos theta, theta dot, so it's theta dot square, and minus r sine theta, theta double dot. So in fact this is also is t square theta by dt. Okay, so this is the first one, minus L cos phi dot square and sin phi dot. Okay, so these expressions keep becoming bigger and bigger. So here we have theta dot square, so it's omega square. Theta double dot is nothing but alpha, which is also given to us. And then we also have phi dot. So we have the phi dot relationship here. So this is, you can use this phi dot. And only thing is that now we have phi double dot. So phi double dot, so it should be can be obtained by differentiating 4. So what we have here, then you take this again. So it is nothing but minus r sine theta, theta dot square plus r cos theta, theta double dot on this side, and we have all minus sine phi dot square plus cos phi. So from this it's very clear that we can get a phi dot here, phi double dot is, so therefore we have this. I'm just writing it completely just for the sake of completeness. So these are pretty long expressions. So we have phi double dot here, and we have So these things can be substituted. So this 7 can be substituted into 6. In 6 to get a relationship, to get an equation for okay. So from this, so you substitute all these things, so they start, the more and more you do the differentiation, so the expressions will become longer and longer. So that way now you can see that, so some of these cases turn out to be simple, and then we will do this one. So this example we will also take it up by some other method, by relative velocities method. So in the last class we were talking about the relative velocities, in the sense that a general motion can be put as a translation plus the rotation. So this we will put it as translation with reference to some point, and rotation about reference to some other point. So this we will take it up in our next class. Okay. So you are going to have a lot of examples like this one. Yeah, I think there's some other variations, and one other case which you keep getting here is that a rolling, which we'll take it up later. So anyway, so for the moment we stop here, and then we take up the analysis of this kind of general plane motion, or as from the point of view of relative motions. So relative motion in the sense that a translation with respect to A, and a relative motion about A, and similarly B. So that is a very general approach by which you can solve not only just one rod, or you can also do this kind of the reciprocating motion in a very systematic manner, and any number of links. So you can have any number of bodies to connect it, and then you can go from one body to the next body and so on. So that's much more general approach. But however, for the sake of completeness, this is the analytical approach. I gave you a hint into this one. So it depends. If you want, you get to this analytical approach if you want to have a kind of programming facility, like you may use the MATLAB, or you can use any other, so that you can get expressions as well as the variation of, for example, AB as a function of theta. So you can just plot as theta changes from 0 to 360, so how AB is going to, in fact, you can find out where it is maximum and where it is minimum, where it can also be 0. So it very much depends upon the lengths R and L, and also the omega and alpha. Okay, so we'll stop it for this moment, and then we'll continue with the next class with the other kind of relative motion approach. Okay, bye for the moment.